So you guys did a very good job. When given an element, you know that the first thing you have to do is figure out how many electrons it's got. You all did that flawlessly. Sodium, for instance, has 11 electrons. You found that because it's got an atomic number of 11, therefore 11 protons. If it's neutral, 11 electrons. And the other thing that all of you did after some prompting was to either draw or dig out this old gem, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 6s, 6p, 7s. We don't have to draw it all the way out because, of course, we're not going that far. What did I just do? Oh, terrible, terrible, terrible thing. And you have to have this, especially when you get up into the bigger elements where you start to have crossovers, to figure out what fills first. Now in sodium with 11 electrons, there are no crossovers. We don't start seeing crossovers until we get up over atomic number 20. So over 20 we start to see crossovers. And you guys all, remembered that 1s, 2s, 2px, 2py, 2pz, zoop, 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 zoop. And sodium also has one out there on the 3s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You guys did a great job. Good. Now, wouldn't it be nice if there was a way to shortcut that? This is, remember, called orbital notation. So what we're writing is the electron configuration for this atom. It's the pattern of electrons in this atom. There are three ways that we write it, and the first is called orbital notation because we draw every stinking orbital. The second is usually called electron configuration notation, so don't get that confused with what we're doing. We're representing electron configuration here too, but we're doing it using orbital notation. The next one that we're going to learn is called electron configuration notation, and it's kind of the middle road. It's not the shortest way you can do it, but it's not the cumbersome, write every single electron kind of way. Okay, so when we do electron configuration notation, we skip writing every orbital, and we just write the name of the subshell. So remember, 1s is both an orbital and a subshell, but 2p is a subshell. Within that 2p subshell, you have 3 orbitals, 2px, 2py, 2pz. 3d is a subshell. Within that subshell, you have 5 orbitals, 3d1, 3d2. You get the picture. So when we do electron configuration notation, we just write the name of the subshell, and as a superscript, we write how many electrons are in it. Let's practice with sodium. Okay, so if we look at sodium's orbital notation, this is a subshell. That's the 1s subshell. We would write 1s2. This is a subshell. It's the 2s subshell. It has 2 electrons. We would write 2s2. This is a subshell. It's the 2p subshell. We would write 2p6. And this is a subshell. It's the 3s subshell. We would write 3s. How many electrons are there? Just 1. So we would write 3s1. Okay? We would write 3s1. So that's the electron configuration notation for sodium. It's expressing the same information as that, but it's a lower level of detail. You know, we don't need to see every single orbital. So let's do aluminum. Aluminum has 13 electrons, and we correctly did the orbital notation, 1s. Oops, let me move that down. Okay, so we got the orbital notation for aluminum, and now if we're going to write the electron configuration notation, we're only writing the names of the subshells and how many electrons are in them. So 1s2, 2s2, all of that becomes 2p6, 3s2, and all of that becomes 3p1. Do not let me hear you say 3s squared. Arr. It's not squared. It's a superscript which indicates how many electrons are present on that subshell. It's not squared. Just a pet peeve. I thought I'd just warn you in advance. Okay, this is pretty easy, isn't it? Okay, so we've written down all the subshells. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. In order to really be correct, we need to reorder those to keep all of the main energy levels together. That's not the order they fill in. 4s fills before 3d. But to write this and really be correct, we need to rewrite it to reflect keeping the main energy levels together. Okay, what that does for you is it easily shows what's your highest occupied main energy level. Not such an issue with this, but we'll do a challenge question out of the lanthanide and actinide series, and you'll see it becomes a big challenge. So that should be your final answer. Now, if you hand me this, am I going to beat you up about it? Probably not too much, but I'll make a mark. I'll make sure you know that you missed that, but I probably won't beat you up on points too badly. Okay, let's do some practice on your own, and I'll spy on you. Okay, so go ahead and do the electron configuration notation for those 4, and I'll circulate and spy on you. Oh, here's a question somebody asked in the other class. Can we do the electron configuration notation without drawing the orbital notation? You can. You probably can't right now, though. I don't draw the orbital notation anymore. I haven't for a long time. But to start off, most of you will probably still draw the orbital and then shortcut it. As you get more fluent with this, you'll probably start skipping that step. If you're doing the orbital notation, if you're not doing the orbital notation first, having that little diagram is going to be essential for larger stuff to make sure you don't stick electrons in the wrong subshell. Okay, so we've got neodymium here arranged in the order that they fill, and then if we rearrange it in order of main energy level, it looks like this. And the compelling reason to do that, of course, is so that you can see that the 6th main energy level is the level that's currently being filled. It's a nice handy visual shortcut. Okay, time to work and then FIP quiz.